Hi, so we're up to Chapter 2 of ENSA, so Enterprise Networking, Security and Automation, and so we're talking about OSPF configuration. So we're going to talk about setting the router ID, point-to-point OSPF networks. We're going to talk about multi-access OSPF networks. We're going to look at modifying how OSPF behaves, so changing some of the default settings. We'll look at advertising default routes, as well as verifying that it's working as required. So, setting the router ID. So to start with, we've got a bit of a standard topology we're using. So there's 3 routers joined together by a point-to-point Ethernet link between each of the routers, and then there's a LAN hanging off of each one as well, and there's a loopback interface we're going to use for the internet. So basically, it's going to be single area OSPF, and so it'll all be part of area 0, and so that's the basic setup that we're going to create. So it's all been configured. Addressing wise, we just need to add the OSPF configuration. So how do we start configuring OSPF? And so in global config mode, if you type in router OSPF and then a process ID number, that will actually start an OSPF process. Now, the number is only of local significance, and so it doesn't matter if neighbours are using different process IDs, they will still communicate. They don't compare process IDs when forming adjacencies. So as you can see, also, once you've typed the command in, you change modes to router config mode, and then the demo here actually has a question mark, and so this shows all the commands that are available. And so the major one we're looking at the moment is that bottom one, router ID. And so that's one way that you can specifically set a router ID, and that's the preferred method. Now, a router ID is a 32-bit value. Of course, because it's a 32-bit number, we just identify it like an IP address. And so it needs to be unique for each OSPF router, and that's how they identify with one another. If an OSPF process can't find a router ID, it will actually not start the process, and so it will fail. So that's one of the reasons why having a reliable source of a router ID is preferred, and so that's why that router ID command is the preferred solution. Okay, so the router ID is used to participate in synchronization of databases, and so the router with the highest router ID will actually be the one that will start that process first. And of course, it can also be a tiebreaker in the election of designated routers as well. And so again, the one with a higher router ID will become a designated router if no priorities have been set. Okay, so as I said, there's several ways you can set a router ID for a router. The preferred one is that router ID command in router config mode, because that's explicitly, well, that's what the administrator wants, and so that's pretty easy. If that hasn't been done, the router OSPF will then search for any loopback interfaces that are available, and if there is one or more, it will actually pick the higher address of those. If there are no loopback interfaces, it will then look at physical interfaces, and those interfaces actually need to be up, otherwise it might use the IP addresses. And so that's actually why we prefer either router ID or loopback interfaces, because that's a more reliable way of assigning a router ID. So, of course, a loopback interface is a way you can do it, and so as you can see here in the config snippet we've got, you interface loopback 1, and then you go into interface mode. You can set an IP address, and as you can see there, it's got a 32-bit mask, which means it's a host address, not a network address. And so then after that, if you start OSPF, the router ID would be that, if you haven't done a router ID command. And so, of course, as I said, the preferred way is the router ID command, followed by what ID you wish to set. And so they've gone the simple route here. Router 1 is 1.1.1.1, and router 2 is the 2s, and router 3 is the 3s. And so that's a sensible way of doing things. Now, that's basically the first thing OSPF does when it starts, is it picks a router ID. So after it's selected that, an active OSPF router does not allow the router ID to be changed until the router is reloaded or the OSPF process is reset. Clearing the OSPF process is the preferred method to reset the router ID. So here we've obviously got a router ID that we didn't want. It's 10.10.1.1. They put in the command to set it to all the ones, and it actually would not change anything until you do clear IP OSPF process, and that will actually stop OSPF, start it again. It will pick up this configuration command and set it as such. Okay, point-to-point links. Now you can actually change the network type of network. So, you know, if you've got an Ethernet interface, by default it will be set as a broadcast network. Now, of course, you can set up an Ethernet as a point-to-point if you just have one cable and, of course, one host at either end. It effectively becomes a point-to-point link, and so so that's useful, and so you can actually change it. I think it's in a later slide. Now, to get it working on OSPF, you just need to do a network command. So network, and then you supply the network address. Now there's the wildcard mask, which I think we'll talk about in the next slide in more depth. And because OSPF is a multi-area protocol for that scalability, you also need to tell it what area every one of those networks is in. And so, of course, we're only talking about single area OSPF at the moment, so we'll use area ID 0. Now, I think there's a bit of a problem on the slide here, but anyway, the wildcard mask is typically the inverse of the subnet mask configured on that interface. Now, if you've done access control lists before, you will have seen wildcard masks. And so basically your wildcard mask is used in the comparison of addresses, and wherever you've got a 0 in the wildcard mask is where you actually want the bits to match, and wherever you've got a 1 in the wildcard mask, in binary of course, that is where you don't care if the bits match or not. Now here, basically this should be a 0 here for the wildcard, the subnet mask. Early versions of the slides do have the odd error here and there. And this is supposed to be a /26, and so it would have been 255.255.255.192. But yeah, they've blown it, and there wouldn't have been a 25 there. 255 there, it would have been a 64. Anyway. Now, within routing config mode, there are two ways to identify interfaces that will participate in OSPFv2. And so basically, in the first example, the wildcard mask identifies the interface based on the network addresses. Any active interface that is configured with IPv4 address belonging to that network will participate in the routing process. And so this is the example here. And so this is where we've used that inverse of the mask. And so I'm assuming this is a 24-bit network mask. And so the first 24 bits are 0, the last 8 bits are 1s. And a member of area 0. This one here, I'm assuming would be your point-to-point links, and so it's a 30-bit mask, and so the last 2 bits are the only ones that you don't need to compare. That is, of course, one way to do it. The other way is actually to specify the IP address of a particular interface, and then do 32 bits worth of zeros. Of course, that implies that, yes, we're talking about a host address. So it actually looks for an interface that has an address that completely matches that. And so that's another way of doing it. Again, because we're single area, it's always area 0. And so this, of course, the advantage of this way is that you don't have to calculate masks. And so you can just grab an address, put quad 0, and it'll work. So that is certainly another option. Now, there is a third option of being able to do this, and you don't actually need to use network commands, and this is more the word has slipped my head. Yeah, it's more consistent with how IPv6 does it. And so you actually go to the interface and go IP OSPF10, which of course is router OSPF10, and so you're matching the process ID, and then area 0 in each individual interface. And that the end result of this is exactly the same as this here. Now of course, you need to identify all of your networks that you want advertised using OSPF, either with the network commands or those interface mode commands. Now, that's fine, but once you've done that, it will actually send packets out each of those interfaces, trying to discover routers and of course, then share details. And so, if you've got a subnet that is completely just for hosts, no routers running OSPF on there, you can actually set that interface to be passive interface. And so that will stop it from attempting to form adjacencies on that interface. And so it saves bandwidth because, well, there's less packets going over the network, and especially packets that aren't achieving anything. Inefficient use of resources. So basically every time a router sends out a multicast, the hosts will see that, and so we'll have to do some processing. Normally it will just be on the NIC, but there will be some processing. And then of course another problem can be that someone might actually have some malware, or some server operating systems actually will support OSPF because it's an open standard, and so they might actually form an adjacency, and then they could of course cause some security problems for the network. And so it's good on several levels having passive interface. Okay, so how do we do it? And so you go into router config mode and type in passive interface and the name of the interface. So here of course we've got loopback, but it could have been G00 if that was a subnet that didn't have any hosts on it. And it does actually list in the show IP protocols, it actually does list what interfaces have been set to passive. Okay, so point-to-point networks. By default, Cisco routers elect a designated router or backup designated router on Ethernet interfaces because they're normally a multi-access network. And so that is good for efficiency on a multi-access network. But if you're using a point-to-point link on Ethernet, well, then it's actually going through a process that it doesn't really need. And so, as I said, Ethernets are normally broadcast by default, but you can actually set them to be point-to-point. And so you go into config mode, you go IP OSPF network point-to-point. And so then it will actually, you're telling it that there's only going to be one other router over there, and so it doesn't need to elect DRs and BDRs. So we will talk about that process more later. Okay, loopbacks and point-to-point networks. Use loopbacks to provide additional interfaces for a variety of purposes. By default, loopback interfaces are advertised as /32 routes, but you can actually set a loopback interface to be a point-to-point interface, even though it's not going to be in reality. But basically, it will change the way that OSPF behaves and will actually advertise the network as the mask has been set. Okay, so multi-access network or broadcast is of course your most common one. And so here we've got a slightly different setup for OSPF. We've got 4 routers and they all are communicating via a central switch. And so, and that is where DRs and BDRs are required. So multi-access OSPF networks are unique in that one router controls the distribution of link state advertisements. The router that is elected for this role should be determined by the network administrator through proper configuration. Now, of course, we spoke about that election earlier, that a tiebreaker is the router ID, but there is actually a preferred way of setting the DR and BDR, and that's using interface priority. Okay. So in all multi-access networks, OSPF elects a DR and BDR. The DR is responsible for collecting and distributing all link state advertisements sent and received. The DR uses the multicast IPv4 address 224.0.0.5, which all OSPF routers listen on. When other routers talk to the DR, they actually use DR's listed on that address and also 224.0.0.6. So a DR is a central sorting station basically for that network. And there is a BDR, backup designated router, and it is, as the name suggests, a backup that will take over instantly if the DR were to fail. And so normally it would be detected by hello packets stopping. If you actually do shut down a router gracefully, it will actually send out a disassociate message, and it will happen instantly. But of course, with a normal failure, it will have to wait for the dead time to go past. So of course, with the DR other, which is a router that's not a BDR or a DR, they will always talk to the DR using 224.0.0.6. And so in the multi-access topology shown in the figure, there are 3 routers interconnected over a common network. Because the routers are connected over a common multi-access network, OSPF has automatically elected DR and BDR. Now, because there's been no priority set, router 3 has the higher router ID, router 2 has the second highest, and router 1 has the lowest. To verify the roles of OSPFv2 router, use the show IP OSPF interface, and it will actually tell you. In this case, we're looking at router 1, so its state is DR other, so it's other than a DR or BDR. But it also tells you which is the designated router, which is the backup designated router. Next slide is actually R2, and so it is the BDR, and it's also it will tell you what the designated router is, and it will also tell you what other neighbours it knows. And so this is on router 3, so this is the designated router, and so it will tell you about the other routers. Now, to verify that the adjacencies are working properly on a multi-access network, you can do show IP OSPF neighbour. So the state of neighbours in multi-access networks can be as follows. So basically, you can have full DR, full BDR, full DR other. Now this option will actually only be on a DR or BDR. This will be all routers other than the DR, that's how they will be talking to it. And this is all routers other than the BDR, that's how they talk to it. Now, 2 routers that are actually not DRs or BDRs don't actually make a full adjacency. They actually make just a two-way. They see each other's hello packets, but they don't actually go to a full adjacency because they don't need to. They really only have to talk with the DR and, for safety's sake, the BDR. Okay, so we're looking at router 2, and so of course it's the BDR, and so its neighbours are the DR and a DR other, and so that's what I meant by that. And so, and this is telling you the dead time, which says in 31 seconds, if I don't see another hello packet, this will be dead. But of course, you know, the dead time is typically 40 seconds, and so if all is going well, the dead time will not really go below 30 seconds. And so they haven't, so everything seems pretty happy. Now, the default DR BDR election process, and as I've mentioned before, there is the interface priority. Now, by default, all routers interfaces are set to a priority of 1, and so if you haven't changed any router priorities at all, that will be a tie for everyone, and that's why the router ID is how it's decided. Now, it's not a great way to do it. Now, if you set the interface priority to 0, it means I do not want this particular router to be DR or BDR ever. But some number, the higher the number, the better chance it will have of becoming the DR. And so, yeah, as I said, if there's a tie, which is the default behavior, that's when they use the router ID. So the election process takes place when the first router on OSPF-enabled interface is active on the network. If all if all of the routers on the network have not finished booting, it is possible that a router with a lower router ID will become DR just because it was first. The addition of a new router does not initiate a new election process. So basically, there's only a new election if there's a need for it. And so normally that would be a DR failure. And so basically the DR is elected, it remains DR until one of the following events occurs. The DR fails, or someone stops or restarts the OSPF process. And so all the multi-access interfaces on DR fails or is shut down. If the DR fails, the BDR is automatically promoted to DR. This is the case even if another DR other with a high priority is added to the network after initial DR-BDR election. That one with a high priority will end up being BDR. So how do we set it? So it's IP, OSPF priority, and a number. And so again, 0 through to 255. So in this instance, we're actually setting the priority to be 255. So R1 will end up being DR. Now, clear IP OSPF process is the way you can do that. Okay. Now, this is how we modify how it behaves. And so the first thing it's going to talk about is the reference bandwidth. Now, reference bandwidth is used to calculate the cost. And so that's the metric, of course, that's used to make routing decisions. So the reference bandwidth by default is 100 million. So 100 megabits per second, that's the bandwidth. Now, of course, this was decided back in the 90s when fast Ethernet was exactly that, very, very fast. But of course, we've surpassed that several times now. And so if you have fast Ethernet gigabit or 10 gig Ethernet interfaces, they will end up with the same cost, because the cost has to be an integer, and so it will actually round it to 1, because you wouldn't have a cost of 0. And so it always, now this slide's got a problem as well, because this 10 meg Ethernet should be a cost of 10. These are the ones that would all end up being with 1. So again, another error in the slide. Okay, and so of course, to fix that problem, basically we need to change this number, and so there's actually a command to do that. And so there's the auto cost reference bandwidth command, and so you do that in router config mode, and then you set by megabits per second. And so if you have gigabit Ethernet, you just type in 1,000. So I personally would probably put in 10,000 just in case, just so that, you know, if you do buy a device with a better interface, it will actually won't mean you have to go through all your routers and change it. You can also set the cost manually on all your interfaces, but I don't know. The router is a computer. It does maths quicker than me. And so whichever method is used, it is important to apply the configuration to all routers in the OSPF routing domain. The table shows OSPF cost if the reference bandwidth is adjusted to 10 gig. And so the reference bandwidth should be adjusted anytime there are links faster than fast Ethernet. And so you can do show IP OSPF interface, and it will tell you the cost that's assigned to that interface. And so as you can see, 10 gig Ethernet interfaces will have a cost of 1, and 10 for gigabit, 100 for fast Ethernet, and 1,000 for plain Ethernet, 10 megabit. Okay, now of course the metric for OSPF is actually the cumulative cost. And so basically, if it goes over 3 links, you know, 2 of them have got a cost of 1 and one's got a cost of 10, will end up being a cost of 12 for that particular path. So of course, the shortest path, or the lowest cost, is the best path. You can calculate the cost for each router to reach the end network, and of course check that it's all behaving as it should. And as I said, it accumulates costs, and so in this case you can see that that's the mean distance, and that is the cost for the route, the metric. And so you can put in an IP OSPF cost command in. Now, if a router goes down, of course, with that triangular setup of routers, you've got some, or a link goes down, you have a backup route to the destination, and so you can see that they are working, but of course the metrics are higher, so not as good, but hey, they're there. Now you can also adjust the timing intervals, and so the first one is the hello packet, and so by default it's 10 seconds. If you want something to respond faster to outages, you might want to decrease the hello packet time interval as well as the dead interval. And so the dead interval is normally 4 times the hello. So if you decrease the hello interval down to 5, you could make the dead interval 20. And so it's going to respond twice as fast, I suppose. And that's, I think, what they do in this slide. No, it might be the next one. Where is it? Hello 10, dead 40. That's the default setting. And so, of course, here is with your dead time of 40, and so they're total dead time of 40. These are less or more than 30, so it's all good. And so you can do the command IP OSPF hello interval and IP OSPF dead interval in the interface itself, and then of course you can set the number of seconds. And this is the slide I was thinking of, 5 and then 20, and then from there. Now, of course, that is one of the things that is compared for adjacency is the timing intervals. And so you've actually, on router 1, it can't talk to router 2 because that's the interface that it talks to router 2 on. So you'd actually have to go to router 2 and configure its intervals to match as well. So the neighbor would come up again. But yeah, as I said, it would detect failures twice as fast. All right, so default routes. Of course, the default route is used to route traffic to the internet. And so, of course, normally it's set with a static route, IP route quad 0, and then, of course, forwarding information. That's nice. Do this on router 2 as it shows here. That's the one with that loopback. That's the default route. And so that's good. Router 2 knows how to find the internet. But router 1 and router 3 don't yet. And so you could either do this command and, of course, modify it to point at router 2, or you can get OSPF to advertise the routes by using default information originate. And so because it's got a default route, it will then add that as an update in OSPF, and so the other routers will learn it, which is probably a much better system. So how do you verify that it's working? On router 2 itself, of course, it's a static. And so that's your destination quad 0 and then a 0 mask, that loopback 1. Of course, on the other routers, it's actually learnt through OSPF. E2 means it's an external route. Same route, but of course it's via router 2. And so that's how it will look on the routers that learnt it. So how do we verify OSPF? And so there are some generic commands like show IP interface brief, show IP route, and show IP protocols is another generic command. And so that will tell you whether the IP information is set up correctly. This, of course, will show the routing table, which is certainly useful for OSPF. Show IP protocols will show you what routing protocols are running for IP. And of course, if OSPF is running, it'll tell you OSPF information. Then there are some specific OSPF commands. So show IP OSPF neighbor, show IP OSPF general, and then show IP OSPF interface. And the coming slides will show you what you get out of them. So show IP OSPF neighbor. I think we've been looking at that fairly regularly, and I've got to admit I do when I'm fault finding things. That's one of the first spots I go to. And so as you can see here, we've got full adjacency to 2 neighbors. So that's looking pretty good. And the dead timers are both higher than 30. So pretty happy setup there. So what would cause problems with adjacency. If you've got your addressing wrong, so the subnet masks don't match, that's going to be a bad thing. Hello and dead timers don't match, as you saw in that previous slide. As soon as I changed the timers, the adjacency died. Network types, and so if you've set one end to be point-to-point, the other one's broadcast, they will not form adjacency. And so of course you need to have those network commands or interface commands for the networks to be advertised. Now, show IP protocols, as I said, is a generic command about your IP routing protocols. So OSPF10, in this case, it's got a router ID, it's got those interface commands that are in there, and it's actually telling you what neighbors it's got. So it's got a fair bit of information there. So show IP OSPF is sort of more general information. Tells you router ID, tells you that it's a member of the area 0, which of course is the backbone. Tells you how many times the algorithm, SPF algorithm is run, how long ago it was, so 11 minutes 31 seconds, and some other information. So it's good information. Don't necessarily use it that often, but it's good information. Show IP OSPF interface is good, tells you what types of interfaces are on them, and so on and so forth, and tells you about neighbors and other things like that. Show IP OSPF interface brief is a very quick rundown. I've got to admit I haven't used it often, but it does certainly look good. It's got some good information, all very concise and precise. Okay, so we're at the end of the chapter. So what did we look at? So we looked at setting the process ID by doing router OSPF 10 was the example given. It's a 16-bit number, so quite a lot of options there. Router ID is a 32-bit number, of course. We display it like an IP address. It needs to be unique, and it's used for a lot of things. It's a unique identifier. And so, of course, that router ID can be from the router ID command, a loopback interface, or a physical interface, of course, preference in that order. Of course, then you need to tell the router what networks are participating in OSPF by using either network commands or those interface commands as well. Now, the network command needs to give the network address as well as the wildcard mask and specify what area it belongs to. And so you can also do an interface command as well, as I said. You can set a passive interface to stop OSPF trying to form adjacencies on an interface that it shouldn't be making adjacencies. You can set a broadcast network to be point-to-point, if that's true. And so we spoke about DRs and BDRs and why they're useful on broadcast or multi-access networks. So DRs, BDRs, and DR others are, of course, the roles. The preferred way of changing that is by using the interface priority command. And so, of course, the auto cost reference bandwidth is 100 megabits by default. Of course, that's probably not fast enough these days, so you should be changing that. And so you can either do the auto cost reference bandwidth command for the entire router, or you can do it on you can manually set the cost on each interface. So, of course, you can play around with the hello and dead interval timers. Normally it's 10 and 40, but of course, if you wanted to detect things faster, you can make those times shorter. Now, when it comes to advertising a default route, you can do that. Of course, you need to configure the default route and then use default information to originate, which of course will then advertise the other routers. If you do that, it actually makes that router an ASBR. Didn't actually mention it in the slides, which is Autonomous System Border Router. And so that it's just another one of the titles they use in there. And so, of course, you need to verify that the default route's propagated, and of course, you need to use various commands to actually confirm that OSPF working the way you want. Okay, so I think that's pretty much it. That's the logo. So that's chapter 2 done. I'll see you later for chapter 3. Have a good one.